sensitivity of graph algorithms. So this is based on joint works with so Kumabe, Pampen, Nizim Barma, and Samson Joe. So yeah, well, I think to understand this talk, well, you don't need any deep knowledge, like you don't need any deep like mathematical knowledge. So I hope this is this is accessible to students, and you enjoy. Okay, so let me start. Yeah, so let me start with some preamble. Algorithms have been used in decision making and knowledge discovery in practice, and it's now a part of society, we can say. And these things are studied in like many areas like machine learning, data mining, operations research, and there are many concrete examples of these applications like self-driving cars, spam email detection, and so on. And many of them can be formulated as optimization problems, of course. So that's because that's why we study those problems. And most of them can be, the problem is that most of them can be solved exactly in polynomial time. So they are typical NP hard. So typical studies like instead of trying to solve them exactly, we try to devise approximation algorithms, which work well in like theoretically or practically. But there's some issue when we apply the algorithm developed in theoretical area or practical area to real applications. So so that's the motivation of studying average sensitivity, and that is errors or inaccuracies are inherent in data. That's what we are overlooking. So, for example, the input data so in the input data, some elements may be missing. For example, think of like social network, then nodes are corresponding to individuals, and edges are corresponding to like friendships. So there should be some true graph that represent true friendship networks, true friendship relations. But some people may just lazy to report their friendship, or for some reason they don't want to report their friendship. So what we can observe from from SNS social network service is just approximation to the true relationship. So yeah, in this case, some edges are missing. And another case is time variation. So in social network or in web graph, graph changes over time. So we don't know what is the true graph, or there may not be true graph, the concept of true graph. What we have is just the approximation of true-like graph. So the graph today.
Hey, Yoshi, Professor, sorry to interrupt, but I don't think we can see your slides. So maybe.
Oh yeah. Oh, you can see. Okay.
Now I can. Okay, so I think
I'm making it full screen right now, but can you see it?
yeah.
Maybe
now we can.
Just about.
Oh, now you can see.
Now. Yeah,
no. Oh, sorry about that. So no problem now.
No problem now.
Okay,
yeah, you just have to probably like go to full screen mode, but beyond that, it's good.
Okay.
Thanks.
Full screen mode. So which
right at bottom right, there's a button like the arrows 4 corners. Right next to 98%, there's a button. Or like to the left of it, maybe.
To the left of. So maybe should I?
Or you can just start the presentation. It's fine. Like.
Well, actually, I'm studying. So.
Okay. Sure.
So I'm not sure what's happening. So yeah, sorry, this is my first time to use this Microsoft Teams. Well, no, this is no.
It only takes like 3-4 PhDs to figure it out.
So this is full screen mode in my laptop. So.
Okay, for us, it's showing both it's not full screen, at least to me. Arindam, can you see full screen, or is it still?
It's I can see the slide, and left side there is all the slides. So it's not full screen.
Okay, so it's not full screen. Well, not sure. Okay, maybe
So
I should stop sharing and then restart sharing. Okay, let me try. And okay, let me try. And how about this?
perfect. Yeah, this
Yeah,
is good.
It's enough full
Excellent.
screen.
Yeah,
Okay,
it's full screen. Perfect.
okay,
Thank
okay,
you.
okay. Yeah, okay, thanks. So yeah, so another case that we inject errors or we have inaccuracies is time variation. So the graph today may be different from graph tomorrow, so we don't know true graph. And another case is arbitrariness in data transformation. So we have, for example, we have a bunch of points. Yeah, uh, typical case is like semi-supervised learning, where we have a bunch of points and some points are labeled, and we want to predict labels of other points. And in that case, we just have points. And then typical way to solve this task is like we first construct the graph out of the points, and then apply graph theoretic method on it. Spectral graph, for example, spectral graph theoretic method on it. And when constructing a graph, typically we for each point we use k-nearest neighbor technique. So for example, for each point we compute k-nearest neighbors and add edges to them, and then we construct the graph. But this parameter k is kind of arbitrary parameter. We can choose any k, 3 or 5. There's no true k. So there's some arbitrariness in data transformation. So we don't know which k is the right answer, or there may not be a right parameter there. So we don't know the true graph. So yeah, so what I want to say in this slide is that errors or inaccuracies must be there. But if we want to apply algorithms in practice, we have to handle such situation. So what I thought is like for efficient and safe use of algorithms, the output should not change a lot when the input slightly changes, because that slight change is inherent in data. So here, what I mean by efficient and safe is the following. For efficiency, yeah, it's easy to see. It's costly if resource allocation changes every day. Basically, the output of algorithm is often used in resource allocation. But if the resource allocation changes every day, then basically, usually it incurs some cost. So we want to avoid that. So we hope that the algorithm's output is stable against input change. And another thing is safety. So it's easy to see stability is important in safety if you think of like self-driving cars. So for example, here is the image of typical self-driving car like task. So we are given an image taken by like video camera, and then we want to split the image, or we want to label each pixel of the image, like which part of the image is cars, which part of the image is like individuals or roads. But if it's dangerous if a self-driving car suddenly stops recognizing people who are still there. Yeah, the image changes over time. Of course, the car we are driving or the car the system is driving is moving. So, but yeah, it's dangerous if it stops recognizing people, even when they are still there. Okay, so for efficient and safe use of algorithms, well, I believe the output should not change a lot when the input slightly changes. Okay, so I want to make this intuition more formal. And what I propose here is the notion of average sensitivity. And the definition is very simple. Let me start with deterministic case. I will discuss randomized case later. So let A be a deterministic algorithm that outputs, okay, let's focus on graphs, that outputs an edge or vertex set. So for example, in the matching problem, we output an edge set, right? And the average sensitivity of the deterministic algorithm A on the graph G is the following. We take average over edges. And what we take average is the size of the symmetric difference of AG and AG minus E, where AG is the output of A on G, and AG minus E is the output of A on G minus E, where E is an edge. And yeah, in the matching case, AG is just the edge set, and we take the difference. We see what happens if we delete an edge, and then take the symmetric difference, and we take the average of the size of the symmetric difference. Yeah, so let's do some practice with this notion. Let's consider outputting vertices with degree just at least 10. This is very simple problem. Yeah, but let me do that anyway. So if we delete an edge, then what happens to the degrees is like at most 2 vertices, or exactly 2 vertices, change their degrees, right? So the output changes, the output change is just 2. So the average sensitivity is bounded by 2, because for any edge E, if we delete it, the output change is 2. So if we take the average, it is at most 2, or exactly 2. Okay, so this is a very simple example. And another case is another very interesting problem is SD shortest path. We have a graph on n vertices, and we want to and we also have 2 vertices S and T, and we want to output a path between them. Yeah, or we want to output the shortest path between them. And this problem is very hard in terms of average sensitivity, because let's look at the n cycle example. So we have a cycle of length n, and we have 2 vertices S and T on the opposite side, and okay, and let's say algorithm A outputs P on this graph. So we have 2 paths from S and T, P and Q, and let's say it outputs P. The other case is similar. And yeah, what happens if we delete an edge? If an edge in the path P is deleted, the algorithm must output Q. So the symmetric difference is like omega n, right? And that happens for any edge in P, which amounts which accounts for n by 2. So the average sensitivity is omega n. So for half of the edges, the symmetric difference is omega n. So the average sensitivity is omega n, which is very bad. Yeah. Okay. Right. So it is easy to see that this measures the stability of algorithms in some sense, but there could be many other notions. So I'm going to tell you why I adopted this notion. So another natural sensitivity notion is this worst case or maximum sensitivity, where we take maximum of the symmetric difference size instead of the average of the symmetric difference size. So if we can bound it, that's pretty nice. But the problem is that if you work on this notion, often it is impossible to bound it. So yeah, that's the reason why this is not so interesting notion. So instead we take average. So another related notion is differential privacy. So I don't want to define differential privacy formally here, but intuitively it says that it's a notion for randomized algorithms, and roughly speaking, it says that the output distributions on the graph G and G minus E must be close. That's also natural notion that can measure stability of algorithms, but it doesn't make sense for many graph problems. For example, if we output a path, then we leak the privacy of the edge in it, right? So if we output a path, we can see that there are edges there, which must be hidden, or we don't want to reveal that edges are there, but if we output a path, then we can see that or users can see that there are edges there. So that means that we cannot output a path if we adopt the notion of differential privacy, but then basically we can't do anything, right? So it doesn't make much sense to use differential privacy in this context when we want to output the like path or vertex set or such large set. Yeah, this differential privacy is more tailored to output, I think, scalar value like average degree or number of triangles or something like that, instead of outputting degree sequence or triangles themselves. So in the definition of average sensitivity, I took like average over edges deleted from the original graph, but it is also natural to think about adding edges. That's fine, but I didn't want to do that because many interesting properties of the graph will be lost if we add edges randomly. So, for example, first thing is that we don't know where to add edges. So probably we may output edges like we sample pair of vertices uniformly at random and add an edge between them. But if we keep doing that, degree distributions will change significantly. So in real-world networks, we know it is known that the degree distribution satisfies some nice property called power law. But if we keep adding edges uniformly at random, if we keep adding edges on pairs sampled uniformly at random, then it's getting close to like random graph, so the degree distribution may collapse. Or another thing is cluster quotient, which measures how many or how often how often we have triangle on the three vertices connected by a path of length 2. So this says that this measures how much we have like friend of friend is friend. But if we keep adding edges, we may destroy those properties. Okay. Also, average sensitivity can be defined on objects other than graphs, like strings or some sequences. But for those objects, it is not obvious how we add elements, right? So if we have strings, we can insert some character somewhere in the string, but which character we want to add, it's not obvious, but the direction is clear, right? So I defined average sensitivity using deleting edges. Okay, so another natural extension of the average sensitivity is instead of deleting one edge, delete k edges. That's also natural, and it is right. For example, we can define k average sensitivity as the average over deleting k edges. Yeah, that's natural, and this can be bounded by the average sensitivity defined in the previous slide. So if algorithm A has average sensitivity f of n is the number of vertices, m is the number of edges, then it has k average sensitivity like that. Basically, k times the average sensitivity. So we have trivial bound on k average sensitivity. So we can focus on studying average sensitivity defined with deleting one edge. Right. Okay.
So can I ask a question?
Yeah, sure,
Quick
sure.
question. So the edge addition somehow seems in the sense that G, like one can look at going from G minus E to G, like in the definition that you had given, but and it seemed to me that that's rather symmetric. Like it's like deleting from G is the same as adding to G minus E, but you're saying in the first part here that it's not the case, or am I missing something?
Yeah, so it's somehow symmetric, but we take symmetric difference between A of G and A of G minus E, and E runs over edges in G.
Okay, I get it.
Yeah, so this is not symmetric, right?
Right. So the
AG
average is
fixed.
over E. Okay.
Yeah.
So it's not clear which edge you add, but it's easy clear which edge to delete. Yeah. Okay.
Yeah. Okay, so the goal of the study of average sensitivity, because this slide was used to get some grants, so I have this kind of slide. Review all optimization problems from the perspective of average sensitivity in order to make better use of data. So theoretical goal might be more interesting to you guys here. So we want to understand the trade-off between approximation ratio and average sensitivity of various optimization programs. So we have some trade-off between them. If we just want to reduce the average sensitivity, we can just output empty set, but it doesn't make sense as an approximation algorithm, right? And if we want to get the best approximation ratio, then we can just use the best known approximation algorithm for it. But it typically has large average sensitivity. So there's some trade-off, and I want to get there. I want to figure out what trade-off we can achieve. Right. So let's see some quick example. So that's minimal vertex cover in the 7th. So yeah, what I want to say in this in the next few slides is that average sensitivity adds one more dimension to the study of optimization problems. So in the 70s, it is just known to be NP hard, so we cannot solve it. So it's like zero-dimensional result, and after that, people have considered approximation algorithm for it, and it is known that it admits two approximation. So this blue region is what we can achieve, and this red region is this is Chinese character, sorry, I forgot to translate. So this red region is what we cannot achieve. So assuming unique Ames conjecture, it is known that 2 minus epsilon approximation is NP hard. So we have this one-dimensional picture of the minimal vertex cover. And studying average sensitivity, we can add one more dimension. So this blue region is achievable, and this red region is not achievable. So below 2, we cannot get we can't get 2 minus epsilon approximation, so we still have red region here. And above 2, we have some interesting phenomena here. So for example, look at, let's see this orange line. It says that there is an algorithm whose average sensitivity times approximation ratio is order n, right? So when the approximation ratio is n to the 1/4, then the average sensitivity is n to the 3/4. And if the approximation ratio is n, which is not very interesting, but anyway, the average sensitivity is order 1, so there's some trade-off. So I want to figure out what trade-off we can achieve for this problem. And actually, for this minimal vertex cover problem, I have completely resolved the question. So with the joint work with Joe, we showed that there is a 2 approximation algorithm with average sensitivity order 1. So for the minimal vertex cover, everything is settled. Right. So I want to do this kind of thing for every problem we have studied so far. Yeah. So that gives a lot of direction or a lot of problems we can study. Right. So let's look at some concrete examples. Right. Graph algorithms with small average sensitivity. Okay, let's start with a simple example, minimum spanning tree. I guess you know the problem. Our input is edge-weighted connected graph, and the output is a spanning tree of the minimum weight. So for so we have graph here, and these numbers are weights on edges, and we want to output a tree with the minimum weight, with the minimal total weight. Okay, so for this problem, there are two popular algorithms. One is Prim's algorithm, and the other one is Kraskow's algorithm. And the bottom line here is that Kraskow is better than Prim in terms of average sensitivity. So let's try. Let's recall what frame was. So we pick we select some source vertex, and we keep adding edges of the minimum weight instead to some vertex we have already seen. So starting with source vertex, we add the lightest edge and keep doing that. Yeah. So here, the one is the lightest edge, and we keep doing that, and we get minimum spanning tree. So this is frame, and the classical is somehow different. We sort out edges in increasing order of weights, and we scan edges in that order, and then keep adding them if we can, if it doesn't make cycle. So this is the lightest edge. So we add it to the spanning tree, and we add it, and yeah, we add it and add it. And fortunately, we don't make any cycle, so we get spanning tree here. So that's classical. So that's easy, and I guess you already know. But they are like more or less equivalent in the sense that they output minimum spanning trees, and their running time are almost linear. Also, they are a little bit different. They are almost linear. So in that sense, they are quite equivalent. But in terms of average sensitivity, they are very different. The Formalizing algorithm has average sensitivity omega n, but classical has order n by m. And m is the number of edges, which is larger than n. So this says that classical has average sensitivity order 1 or less. So that's quite small. So there's huge gap between them. And here's the proof sketch for classical. So we have spanning tree output by classical's algorithm. And if we delete, so we want to see how the spanning tree changes after deleting an edge. And if we delete an edge, not in the MST, classical doesn't change anything. So it outputs the same spanning tree. So there's no symmetric difference size. So the size of the symmetric difference is 0. And if we delete an edge in the MST, what happens? Yeah, the classical outputs somehow different spanning tree, but it's very similar. Because the output of the classical is spanning tree, if we delete an edge in the MST, it partitions the spanning tree partitions the graph into two components, right? So the above this red dashed line and the below this red dashed line. And what classical does on the reduced graph is just adding one edge connecting that bipartition, connecting the two parts in the bipartition. In particular, it selects the lightest edge crossing the two parts. So the difference is just 2 because we deleted one edge from the original spanning tree, and we add one edge to the original spanning tree. So the change is just 2. So the average sensitivity is quite small. So that's the first sketch. But because Prim is kind of iterative, has iterative nature, its outputs may drastically different from the original one. Right. So I'll explain a few graph problems and show, study average sensitivity of them. So the next one is global minimum cut. I guess you already know, but
hey, Yuichi, just a quick question for the
sure.
For the spanning tree. Like, do we also understand that we can't go beyond Kruskal? Like, as in, like the one cannot expect. Like, there are other sort of, for example, like Bovruka's algorithm and so on for MST. So, is it?
I guess
is it theta of?
Right. So I guess n by m is kind of lower bound. So because we take the right. So if we delete an edge in the MST, at least we have to change at least one edge, right?
Right. Yeah. Fill that cycle up.
Yeah. So in this, so average can be written as 1 over m times sum of the changes, and the sum will be n, at least n, and because we have denominator m, so I guess n by m is lower bound.
Okay.
Yeah, it is tight. Right. Okay. So the global min cut problem. Here, okay, let me fix some notations here. We have vertex set S in a graph G, and the cut size of S is denoted by cut sub G of S, and that is the number of edges crossing S and B minus S. So here, do we have animation? No. So this is S, and the cut size here is just 2. So here the cut means a vertex set instead of edge set. So in the global min cut problem, we are given a graph G, and the goal is to compute a minimum cut, of course. Yeah. So the output is vertex set. So because in the average sensitivity definition, we use, well, the output representation may like influence the value of the average sensitivity. So fixing the output representation is important here. So here I'm going to use vertex set. Right. So for the deterministic algorithms, I don't have any lower bound, but I couldn't come up with any deterministic algorithm that has low average sensitivity. So let me work on, or let me talk about randomized algorithms, and let me define average sensitivity for randomized algorithms here. So let A be randomized algorithm that outputs an edge set or vertex set. In the min cut case, it is vertex set, and the average sensitivity of the algorithm on the graph G is the following. We take the average as in the deterministic case, and we take the difference between A of G and A of G minus E. But what we take is the earth mover's distance. So what is earth mover's distance? Right. So the definition is here, but let me try to explain. So because A is randomized algorithm, A of G is random variable, but let's regard it as a distribution of over vertex sets. And earth mover's distance between two distributions, in this case A of G and A of G minus E, is defined as this. So we have joint distribution D over pairs of vertex sets. So we can sample a pair of vertex sets S prime from the distribution D, and we take the expectation of the symmetrically defined size. So the distribution D must have some property. Specifically, the marginal distribution on the first coordinate is exactly equal to A of G, and that on the second coordinate is equal to A of G minus E. So we can take, it's like finding best coupling between two distributions, and we take in the distribution we take the expectation of the symmetrically defined size. So that's earth mover's distance, and we take it. We use it in the definition of average sensitivity. Right. Is that fine? Okay. So
this might not be computationally easy.
This might not be computationally easy. Right. Yeah, that's true. Yeah, that's true. Oh, yeah. So given the algorithm you want to compute average sensitivity of it?
Right.
Yeah, yes. That's a nice meta question. Right. Yeah, I've never thought about it. Well, what I have thought about is like design algorithm that has low average sensitivity, but it's also interesting.
Okay.
Yeah.
Even the earth mover distance can be sort of tricky, right? Like the minimizing over joint distributions. Like in some case.
Yeah, in some cases it is hard. If the support size is small, we can compute it using Pro. But if the support size is exponential, I'm not sure how we can compute it. Right. Yeah. Yeah.
But probably sampling and all, you can estimate it close well enough.
Yeah. So, well, I don't insist this is the only right definition of average sensitivity. There could be many variations, but what we studied in our work is this.
Right.
Yeah.
No. Yeah, just a, as you said, just a meta question, not a.
Yeah, sure.
Yeah.
Okay, let's, by the way, how much time do I have? Maybe just 20 minutes from now?
Yes, around 20 minutes.
Okay. So I have to be very quick at some point. So let's try to, let's practice with this notion. So again, let's think about computing ST shortest path. Then in this case, A can be randomized. So let's say the algorithm A outputs the path P with property small p. Then what happens if an edge in P is deleted? Then, so originally we have P property mass of P on the path P and 1 minus P on the path Q. But after deleting an edge in P, in capital P, all the probability mass must be on the path Q. So the atom distance is going to be P times n by, oh, I said n by 2, but it should be, I guess, n, because the symmetric distance is P times n. And if an edge is in Q is deleted, the atom distance, the contribution to the atom distance is with a similar calculation, 1 minus P times n. So the average sensitivity is like with probability half, we may delete an edge in P, then the contribution is P times n by 2 or P times n. And with probability half, we delete an edge in Q, the contribution is 1 minus P times n. So in the end, we get average sensitivity of omega n. So for the shortest path problem, even if we use randomized algorithm, the average sensitivity is high. Right. Okay, so maybe I think I should skip this slide. Yeah, so in this slide, I was like discussing maybe there's another notion of average sensitivity for randomized algorithms, but okay, let me skip it. Okay, so this is the result for global mean cut. Yeah, so for the upper bound side, there is 2 plus epsilon approximation algorithm with average sensitivity n to the 1 over epsilon times opt. So this average sensitivity is quite small when the opt is as large as omega log n. So when opt is log n, average sensitivity is basically constant. And for the lower bound side, if we want to output global mean cut exactly, then the average sensitivity must be omega n. And also, if we want to output some constant approximation to the minimum cut, then the average sensitivity must be n to the 1 over opt. So the upper bound is almost tight. Right. Okay, so let me talk about how we can get average sensitivity of n to the 1 over epsilon times opt using a few slides. Okay, so the idea is the following. Instead of outputting the exact global mean cut, we sample cuts from so-called Gibbs distribution. So here's what it is. We are given a graph and the parameter epsilon, and we first compute the mean cut size of the input graph G. And let's say alpha is a parameter, and it is said to be log n divided by epsilon times opt. And then instead of outputting a global mean cut, we output a cut S. This is a vertex set with probability proportional to e to the minus alpha times cut size of S. And this distribution is called the Gibbs distribution or Boltzmann distribution in statistical physics or statistics, and I'm going to use it. And the intuition of doing that is here. So if alpha is big, then the penalty, if the cut size is large, we have a large penalty here. So we want to output we want to output a large cut. So if alpha is big, the output we get will be close to the global mean cut. And yes, so this is for approximation. And the next thing is about average sensitivity. Yeah, so the cut size, the observation here is so I can see some I can hear some background noise, but yeah. Anyway. So what we can observe here is that the cut size of S differs by at most 1 between the original graph G and G minus E. So the exponent here will be very close between G and G minus E. So if alpha is small, then output S we will output a similar output because the penalty here is very close between G and G minus E. So we want to take the sum. We want to take some balance between these two cases. An issue of this approach, yeah. So this will work, but the issue of this approach is that we can't sample from the Gibbs distribution in polynomial time because it is a distribution over exponentially many vertex sets. So instead, what we do is the following. So we again compute the optimal mean cut size, and yeah, alpha is log n divided by epsilon times opt. And instead of outputting from Gibbs distribution, we first enumerate cuts of small size. Specifically, we enumerate cuts of size at most 2 plus epsilon times opt. And then we output cut S from the enumerated cuts with probability proportional to e to the minus alpha times the cut size. So yeah, similar idea was used in the differential private setting. And good thing of this is that we can bound the time complexity. But first, the approximation ratio is clear. So because we have enumerated two cuts of size 2 plus epsilon times opt, the approximation ratio must be 2 plus epsilon. And here is the thing, the time complexity. So the procedure of sampling, enumerating cuts of size 2 plus epsilon times opt is small because of the following theorem due to Kargar. So for any alpha, the number of cuts of size alpha times opt is at most n to the 2 alpha. And moreover, we can enumerate them in polynomial time per cut. So we can enumerate all the cuts of size 2 plus epsilon times opt in polynomial time. And yeah, so what's remaining is the analysis of average sensitivity. And yeah, in this talk, because the Gibbs and approximate Gibbs are close, so let me focus on analyzing the average sensitivity of the former algorithm, which doesn't enumerate small cuts, but sample from the Gibbs distribution. Okay.
So these are close in the L1 distance or in the Earth mover distance?
Gibbs and yeah, actually L1.
Okay, which is
actually, yeah,
stronger.
L1. Yeah, actually L1. Yeah. You mean total variation? Yeah, yeah, it is small. It is close in with respect to total variation distance, so it is actually stronger. Well, actually, for this problem, we don't need to. Well, actually, we can bound the average total variation distance for this problem, for this particular problem. But for other problems like matching or other things, we need asymptotic distance or like symmetric difference size. Yeah. So the analysis is not very long, but maybe, yeah. Let me mention some idea. Or maybe, yeah, it's not very long, but I think I should skip it. Or yeah, okay. Let me talk about it anyway. So let A be algorithm that outputs that samples a cut from the Gibbs distribution, and let PGS be the probability that A outputs S on G. Then for any cut S crossed by an edge E, PG minus E of S and PG of S have this relation. So PG minus E of S is approximately equal to PG of S times e to the alpha. This is not accurate, but good approximation. And then the asymptotic distance between A of G and A of G minus E can be can be is approximately equal to the following. So for right, so this bounds the total variation distance between the output distribution for G and G minus E, and right, so we take this the sum over sets crossed by E, and the difference is that. So basically here we are taking the L1 distance between two distributions, and for so if they don't agree, then that has contribution to the average sensitivity by n, because we don't know what happens. So we may output a completely different set. So this is a pessimistic bound, but we bound it by n. This is a trivial upper bound on the symmetrically different sides. Then using the above relation, we can rephrase it this way: n times e to the alpha minus 1 times sum of Pg of S over S is crossed by E. And then to compute, so this is the difference between A of G and A of G minus E, and we want to compute the average of them. Then the average sensitivity of A is the following. So here we have n to the exponential e to the alpha minus 1 times sum, and we have another sum over E, and to take the average, we have m in the denominator. And what's interesting in this quantity is that this double sum is just the expected cut size of S in the original, expected cut size of the output of A in the original graph. So we take the average over, we take the sum over E, we take the sum over S crossed by E, and we here we have the probability that we output S. So this is the expected cut size. And we know that it is at most 2 plus epsilon times opt. Well, here I'm cheating because this is about original Gibbs distribution, not approximate Gibbs distribution, but because they are close, expected cut size is close. So it is basically bounded by 2 plus epsilon times opt. And we can upper bound it by, right, so this has, So because opt is at most 2m divided by n, opt and n by m cancel out, and what we get in the end is e to the alpha. And from the choice of alpha, we get the desired average sensitivity bound. So here, looking at this proof, it was important to take average. If this average, so average appeared here as a sum, and if this is not sum but max, then we don't know how to bound it. And it was also important to delete edges instead of adding edges, because we are deleting an edge, we have expected cut size here. Right. So the definition was very good for this analysis. Well, I can't justify the definition this way, but yeah, that's a fact. Right. So let me skip lower bounds and minimum ST cut. So minimum ST cut is interesting because the Kargat's theorem doesn't hold anymore. So we can't use the Gibbs sampling technique because we cannot sample cuts from the Gibbs distribution. So instead, what we did for this problem is thinking about LP relaxation, and then then added regularizer to the LP here, so which is often used in machine learning, and then to stabilize the output. But this is weaker than the global mean cut case. So in the global mean cut case, the multiplicative approximation is 2 plus epsilon, and average sensitivity is n to the 1 over opt, which is very small. But for this ST mean cut case, we have additive error of n to the 3/4, which is pretty big. It's not multiplicative error, it's additive error of n to the 3/4. And average sensitivity is also n to the 3/4, which is polynomial, so that's very big. So the situation is very different from the global mean cut case. Also, we have studied maximum matching, and yeah, let me skip there. Let me skip it. So here the idea is instead of using exact matching algorithm, for two approximation, some kind of greedy works very well. Surprisingly, it has average sensitivity order 1. And to get 1 minus epsilon approximation, we borrowed some idea from streaming algorithm, and the average sensitivity is constant, but it's pretty big. Okay, let me wrap up. So the summary is the following. We introduced the notion of average sensitivity of algorithms. The hope is that we can review all optimization problems from the perspective of average sensitivity again. So there are a lot of things we can do on it. That's good. And a little is known because I just proposed this notion last year or something. So there are a lot of open problems. And but already we have obtained stable average or algorithms with small average sensitivity for few problems like MST or global mean cut, matching, and so on. And the good thing is that we managed to use ideas from different areas. So for example, Gibbs distribution is from statistical physics or statistics. And matching, I've used randomized greedy, and analysis is borrowed from distribution literature, distribution computing literature. So it's not distribution, distributed computing literature. And the regularizer, the idea of adding regularizer to the ST mean cut LP is borrowed from like machine learning. So it is nice to see that these different ideas can be used in the analysis of average sensitivity. And also there are many things that I didn't cover. So we already have stable average algorithm for knapsack problem, dynamic programming, and we also analyze spectral clustering in the perspective of average sensitivity. And there are some connections to local and online algorithms. There are some concrete open problems. So the one thing is that is there any better algorithm for ST mean cut? Currently, additive error is in the slide it was into the 1/3, but in the paper we got into the 2/3, but still big. So I wonder whether we can get much better approximation guarantee and average sensitivity. And also, I wanna obtain methodology for obtaining lower bounds like Yau's minimax lemma for property testing or communication complexity for streaming algorithms, but we don't have it. Currently, it is very, very problem specific, and also we don't know how to get strong lower bounds for approximation algorithms. So that's a big challenge. Also, the motivation of studying average sensitivity is coming from practical use of algorithms. So I want to check whether it is very useful in practice, like adversarial training is useful in the study of deep learning. Yeah, okay, that's it. Thanks. So is there any question?
So thank you for this
Thanks.
beautiful talk. Are there any questions? We have time for some questions.
Hey, Yuichi, just a quick, so the other lower bounds, even the specific ones, are they robust to sort of graph families? So in particular, like going back to the shortest path example, it seemed like cycle was literally the worst possible. So let me pose a more specific question. Let's say I start off with a G that's known to be, say, an expander or has some nice property. In that, so are there like specific lower bounds known even then?
Yeah, so in the expander, maybe if the graph is expander, the average sensitivity can be made low. Yeah, that's my guess. I haven't analyzed, but that's my guess. But I guess you're talking about shortest path, right?
Yeah,
so
now.
Yeah, if the graph is expander, there are many short paths between S and T. So we can think about distribution over those paths.
Right.
And yeah, I think it can be made stable on average, but yeah. So
Okay.
yeah. So it's not very robust against graph classes.
Yeah. Okay. And this probably like is true for ST cuts and all as well, like where you. Yeah. So okay, the trouble there would be that the minimum ST cut is close to, is just the S or T itself. But I'm hoping if with some approximation
Mm-hmm.
factor, you can just sample good enough. Yeah. So
Okay.
this.
Yeah, but for the ST min cut, I guess there's, well, I don't know. I have no way. I don't have any method to show lower bound for the ST min cut problem if you
Uh,
if you allow for approximation, and
uh,
also I don't have any way to get. So I hope there is much better algorithm in terms of average sensitivity as well as approximation ratio, but yeah, I don't know.
Right. So, and like again, more of a like a philosophical or meta question. So, in somehow it was kind of interesting to me to see that like Prims and Kruskal behaved rather differently. Like
Yeah,
you would
yeah.
not. This is not I mean, okay. Of course, like you once you go through the analysis, you see why. But is there an understanding of like some other properties of
Mm-hmm.
the algorithm that imply? So
Yeah,
it's
yeah, 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 there is. So in this slide, yeah. So I mentioned that there's some connection to local algorithms. So
uh-huh,
here, yeah, so this means that if we have some local or sublinear time algorithm on some problem,
uh-huh,
then that means that the output of the sublinear time algorithm won't be affected by small change in the graph, right? Because it doesn't look
uh-huh.
at those parts. So if we can, if there's a global algorithm that the local algorithm simulates, then
Uh-huh.
the global algorithm is stable.
Okay. Okay, that's
So
interesting.
yeah, so for the maximum matching problem, I used to use sublinear time algorithm for maximum matching to get stable on average algorithm
Mhm.
for maximum matching. But after that, we noticed there's a way to improve it. So I didn't,
Oh,
yeah, discuss it here in this slide. But yeah, originally the algorithm for maximum matching was obtained by translating or transforming sublinear time algorithm for maximum matching.
okay. And since like final question, and then I'll shut up. Like, is there a like? Do you think there's a connection in the other direction as well? That is, like, and maybe for lower bounds, like showing that low average sensitivity would imply the existence of such an algorithm.
Uh,
So in particular, saying that there's no local, like there's no sublinear for ST mincut is a good evidence for
mm,
sensitivity being high.
since right, so the other direction. So that means that uh, if there is a algorithm with small average sensitivity, then there is a sublinear time algorithm. But
Yes, or a local algorithm.
um, that might not be true, right?
Yeah, the Gibbs sampling one sort of rules it out, I guess.
Yeah, yeah. So I think it's a strict subclass
Okay,
in some sense. Yeah.
okay, thanks.
Yeah. Thanks.
Yeah, I have one question.
Yeah.
Pardon my ignorance here. So, is the average notion of average sensitivity a characteristic of the problem or the characteristic of the algorithm actually?
Well, actually, both. So if you pick up one algorithm, then you can study average sensitivity of it. But the trade-off between approximation ratio and average sensitivity is the characteristic of the problem. So we're actually both.
Okay, so the reason I'm asking is, so you initially pointed out an example of ST shortest path where you gave an example where if you remove one edge, you'll have to just use the other shortest path, which
Yeah.
has like all the edges are being replaced.
Mhm.
But whereas as Siddharth sir pointed out right now, so it's possible to have some other problem instances or some other graph instances where the change might not be so bad. The number of edges getting replaced might not be so bad.
Yeah.
And in another case where you have the minimum spanning tree problem, so one algorithm performs well and one algorithm does not perform so well. We have algorithm dependent bounds there. So that for a given problem, two different algorithms perform in two different ways.
Yeah.
Whereas in the other problem, two different problem instances perform in two different ways, irrespective of the algorithm. So that was my understanding. So actually, when does this notion of average sensitivity start being dependent on the algorithms for a particular problem, and when does it really depend on the problem instance for a particular problem?
Okay. So well, maybe you can think about like approximation ratio. So approximation. So for general, so I don't have any good example here, but people have studied approximation algorithm for some particular graph classes, right? So like planar graph, we can get constant approximation, but for general graph, we can only get log n approximation or more, something like that. So if you restrict graph classes, then I guess average sensitivity can be improved. That's a natural phenomenon, I think. So yeah, sorry. So what was your question? Maybe am I answering?
Yeah. Okay. So let me try to just quickly give another example. So for example, in the maximum matching problem that you had,
yeah,
I can sort of visualize that if you actually remove an edge from the graph that was a part of the matching, it has a kind of a ripple effect where like a lot of other edges get toggled in the maximum matching. So so the visualization is that like you have one edge and then you don't have one edge in the matching and then you have another edge. So it should be something like that, right? So once you remove one edge from the matching, all the other edges that kind of form a chain from that, like all those edges get toggled on the whether they are in the matching or not in the matching.
Yeah.
So in that problem, I can visualize that irrespective of the problem instance, like for most of the problem instances, if you just remove an edge from the matching, it's going to have a large sensitivity. The output is going to change drastically.
Okay.
So in that problem, I'm able to visualize that. Whereas for some other problems, like the ST shortest path or the minimum spanning tree, I'm not able to visualize so clearly on how it can have a large sensitivity. So there are a few algorithms that perform well and few that don't. So I'm just wondering, like, how much of it is the inherent characteristic of the problem itself, and then where it is an inherent characteristic of the problem instance.
I'm not sure about the maximum matching. Well, seemingly you are right on the maximum matching problem, but for some, there could be some tricky graph classes on which the maximum outputting maximum matching has low average sensitivity. So I'm not sure. Right. So, but yeah, but right. Yeah, but yeah, in general, I think outputting path has a high average sensitivity, like shortest path or like TSP or something like that. But how can we formally explain it? Yeah, I don't have a good answer for it. So that could be a good open problem, but yeah.
Okay.
Yeah. So what we can say for maximum matching or other problem is like we can locally fix. Yeah, maybe it's not local, right? Yeah, maximum matching is not local, but 1-epsilon approximation to the maximum matching is very local thing. So if you have matching, the graph changes locally. The graph changes a bit, so you have to change the matching. But if you're happy with 1-epsilon approximation, then the change is very local. So, but there's no formal notion of this local nature of problem, right? So it's hard to answer your question.
Sure.
I have another question. So, is there a connection between smooth complexity and sensitivity analysis? So, if a problem has smooth analysis or
smooth analysis. What is known for smooth analysis? So what I know is just the LP simplex, and Any other example, like tensor compression or something?
Yeah, I also know about LP, not much. But if you know for a problem, the general complexity, smooth complexity are kind of far away. Does it say that sensitivity of the problem is high?
Right. Smooth complexity basically bounds time complexity instead of average sensitivity, right? So how can we rate those two things? Yeah.
No, I think what Arindam is asking about is like the condition number of the instance.
Okay. Condition number is close, right? So you're saying that if you perturb the matrix, then if you solve the LP involving that matrix, you get better average sensitivity. Yeah, that might be true. Yeah, because the condition number is small. Yeah, but I'm not sure we can say something interesting out of it. Yeah, there are a lot of like perturbation theory in matrix analysis, so we can use these things to analyze average sensitivity of LP so far. But actually, in my paper with Pan on spectral clustering, we have used some techniques from matrix perturbation theory of matrix. So yeah, in a sense, condition number is very important. Condition number was very important. So yeah, in a sense, perturbation will work well. Yeah.
Thank you.
Okay, let me stop the recording and then we can have a more informal discussion after this.